deep foundations. When the soil at the shallow depth is not having sufficient strength to take care of the structural loads, then deep foundations are used to transfer the load to the deeper strata. There are three types of deep foundations: pile foundations, wells or caisson foundations, and drilled pier foundations. Piles are the long slender members, either driven or cast in situ. They may be subjected to vertical loads or lateral loads, or sometimes combination of both vertical and lateral loads. Wells are also called as caisson foundations, which are heavier in section and they sunk to the required depth. They are normally used to carry very heavy loads, such as the loads from the bridge piers or multi-storied buildings. Sometimes the term drilled pier is used for the piles of a bigger diameter of more than 1 meter, and they may go up to 5 meter or more. They are nothing but large diameter board piles which may be built at the bottom to give greater bearing area. The design principles of drilled piers are the same as that of piles. Piles are also used to take up uplift loads. Piles may be used as a single pile or in groups with vertical and batter piles. Types of piles. There are various classification systems available based on the composition, based on the method of installation, based on the load transfer mechanism, based on the use, based on the displacement of soil, based on the shape of pile, and also based on the size. Based on the load transfer mechanism, the piles are classified into three types: end-bearing piles, friction piles, and combined end-bearing and friction piles. Load transfer mechanism. When the load is applied on the pile, then part of the load will be taken by the soil surrounding the pile shaft and part of the load will be transferred to the pile tip. So whatever the load that is taken by the soil below the pile tip is called end bearing load, and the load taken by the soil surrounding the pile shaft is called frictional load. So initially when the load is very small, the entire load will be taken by the soil surrounding the pile shaft. When the load is increased, the frictional resistance will be fully mobilized and the load will be transferred to the pile tip. And further, if the load is increased at a certain point, the end bearing resistance also will be utilized completely and then the pile will fail. So corresponding to ultimate load, it is equal to the sum of end bearing resistance and frictional resistance. So which can be written as end bearing resistance multiplied by bearing area plus frictional resistance multiplied by surface area of the pile. So in case of pile foundations, the factor of safety will be taken as 2.5. So allowable load or working load equal to ultimate load divided by 2.5. If the end bearing resistance and frictional resistance are obtained separately, then we can take separate values for factor of safety. For end bearing resistance, the value is 3 and frictional resistance 1.5. So that we will be getting another value of working load. So design working load can be taken as smaller of these two values. So there are various methods available to find the ultimate load carrying capacity of a single pile by using static analysis, by using dynamic methods, by using SPT and CPT values, and also by using field tests such as pile load tests. Static analysis. There are various methods available to find the ultimate load carrying capacity using analytical solutions. So ultimate load is the sum of end bearing resistance and frictional resistance. So end bearing resistance is nothing but the bearing capacity. So we can write it as CNC plus Q naught dash NQ plus 0.5 gamma D N gamma into bearing area. Then frictional resistance alpha into Cu bar into AS plus sigma K into sigma VA dash tan delta ASI. So here Cp is the average cohesion of the soil at the pile tip. NC value always we should take it as 9. Q naught dash is the initial effective overburden pressure at the pile tip. NQ and N gamma are the bearing capacity factors corresponding to the given phi value. Gamma is the unit weight of soil at the pile tip. D is the diameter or width of the pile. And AB is the bearing area of the pile at the pile tip. Alpha is the adhesion factor. Cu bar is the average cohesion. As is the surface area. So here K is the coefficient of earth pressure. Sigma Vi dash is the average effective stress corresponding to a particular layer. Then delta is the angle of wall friction between pile and soil. And ASI represents the surface area of the pile in ith layer. So for the piles in granular soils, we have to ignore the cohesion contribution. So we have to ignore those two terms which are related to the cohesion. So these two terms will not be there. That is CNC and alpha Cu bar into AS. These two terms will not be there if it is a granular soil. So in case of granular soil, we have to take the delta value. Delta value 3/4 of pi for concrete piles and 2/3 of pi for wooden piles. So here K value, K is the earth pressure coefficient which is equal to 1 for the phi value less than or equal to 29 degrees and it is equal to 2 for the phi value greater than 36 degrees. Generally we will be taking between 1 to 3 for loose to medium sands. In case of cohesive soil, then we have to ignore all the frictional terms and we will be taking only the cohesion contribution. So in case of piles in cohesive soil, the ultimate load carrying capacity equal to CNC into AB plus alpha Cu bar into AS. So N value, based on the N value, we will be finding the alpha value and for different types of soft soils, the alpha value is given as 0.3 to 1. Then to estimate the Q naught dash value, we will be using the critical depth concept. So according to basic, the Q naught dash, that is the initial effective overburden pressure, increases linearly up to a limited depth only, beyond which it remains constant. This depth is called critical depth. So this critical depth can be determined using the ratio LC by D. So in case of phi value less than or equal to 30 degrees, then this ratio equal to 15. That means critical depth equal to 15 times the diameter. In case of phi value greater than or equal to 40 degrees, then critical depth equal to 20 times that of diameter of the pile. So we have to find the Q naught dash up to the critical depth only. Just check with the numericals. Calculate the safe load carrying capacity of a circular pile of 300 mm diameter, 6 meter length driven into a layered soil. The top layer is 2.5 meter deep clay with phi equal to 0, C equal to 30 kPa, gamma equal to 14.5 kilonewton per meter cube and alpha equal to 0.8. Second layer is sandy soil which is more than 6 meter thick with the C equal to 0, phi equal to 20 degrees, gamma equal to 15.5 and delta equal to 15 degrees. Use NQ equal to 10, N gamma equal to 5.39 and factor of safety equal to 2.5. So here there are two types of soils and top 2.5 meter thickness is a clayey soil which is having C equal to 30, gamma equal to 14.5. But the second layer is cohesionless soil since C is given as 0. So to find the ultimate load carrying capacity, first we should write the equation of IS code where QU equal to CNC plus Q naught dash NQ plus 0.5 gamma D N gamma into AB plus alpha Cu bar into AS plus sigma I equal to 1 to N K into sigma VA dash tan delta I ESI. So here the first term represents the end bearing resistance. So we have to take the soil properties corresponding to pile tip. So corresponding to pile tip, C value. Since the second layer is cohesionless soil, there is no C value, C equal to 0. So this term will not be there, CNC term will not be there. Then Q naught dash NQ. To find the Q naught dash value, we should find the critical depth. So here critical depth is based on the phi value corresponding to pile tip. At the pile tip, the phi value is 20 degrees. So which is less than 30 degrees. So we should take it as 15 times that of diameter. So 15 into diameter is given as 300 millimeter, which is 0.3 meter. So we'll be getting the critical depth as 4.5 meter. So we have to find the Q naught dash value up to 4.5 meter only. So first 2.5 meter is having unit weight of 14.5. So 14.5 into 2.5. In the second layer, remaining depth, total depth is 4.5 meter. So remaining is 2 meter, 2.5 plus 2, 4.5. So remaining 2 meter is having unit weight 15.5. So the value is 67.25. Then here NQ value is already given. Gamma value is corresponding to pile tip. Diameter is given. N gamma value is also given. Area of the pile at the pile tip is nothing but pi by 4 d square. Then alpha value is given. Cu bar, average cohesion. Average cohesion, since the cohesion is same, we can take it as the same value. Then K into K value. K value is not given. So we have to assume the value. Sigma VA dash. Average effective stress. To find the average effective stress, we have to prepare the effective stress diagram. Then tan delta. Delta value is given. Surface area is nothing but perimeter into length. So here average effective stress is calculated for the second layer because first layer is cohesive soil. First layer is cohesive soil. So no need of finding the average effective stress because this term will not be there for the first layer. We have to use this equation for the first layer and this one for second layer. So now when we substitute the values, here C value at the pile tip. At the pile tip, there is no C value. So this term will not be there. So Q naught dash value is calculated. So Q naught dash into NQ plus 0.5 gamma D N gamma into AB. Area of pile at the base, it is pi by 4 d square plus frictional resistance. To calculate the frictional resistance, we have to take each layer separately. First layer is cohesive soil. So we have to use only this term alpha into Cu bar into AS plus second layer. Second layer is cohesionless soil. So we have to use this part of equation where K value is assumed as 1.5 and sigma Vi dash average effective stress for the second layer it is 36.25 plus 90.5 divided by 2. So that value multiplied by tan of delta into surface area, perimeter into length. Length of second layer is 3.5. Length of first layer is 2.5. So that we can calculate the ultimate load carrying capacity of the single pile. Then safe load or allowable load equal to ultimate load divided by factor of safety. So factor of safety is given as 2.5. So taking the factor of safety as 2.5, we can calculate the safe load or allowable load. Another example, calculate the safe load carrying capacity of 500 mm pile driven up to a depth of 15 meter. The soil properties are the soil is loose sand up to 2.4 meter from the ground level with thereafter the soil is dense sand with phi equal to 30 degrees, gamma equal to 17 kilonewton per meter cube and delta equal to 15 degrees. Assume K1 equal to 1.5, K2 equal to 2 and factor of safety equal to 2.5. So here, since the soil is corrosionless soil, we can take the equation of granular soil. So here we have to calculate the critical depth to estimate the Q0 dash value. So critical depth is taken as 15 times the diameter because the phi value is 30 degrees. So it is coming as 7.5 meter. So we have to find the Q0 dash corresponding to 7.5 meter depth. So the value is coming as 127.5 kPa. Then ultimate load carrying capacity can be calculated using this equation. So where it is coming is 2752.565. So allowable load equal to ultimate load divided by factor of safety. Another example, a concrete pile of 45 cm diameter is driven to a depth of 16 meter through a layered system of sandy soil. The following data is available. Top layer, layer 1, layer 2, layer 3 properties are also given. So here we need to calculate the allowable load on the pile. Factor of safety is given, delta value, NQ value and gamma values are given. So there are 3 layers. For each layer the soil properties are given and all the layers are corrosionless soil only. So we should take the equation for granular soil, and here first we should find the value of critical depth, as we need to find the Q0 dash corresponding to critical depth. And here since the phi value at the pile tip is 38 degrees, the critical depth equal to 20 times that of diameter. And we have to prepare the effective stress diagram to find the average effective stresses corresponding to each layer. Then we have to find the delta values corresponding to each layer by taking it as 3/4 of phi. Then we have to substitute all the values in the basic equation, where we have to calculate the end bearing resistance multiplied by bearing area plus frictional resistance of first layer, then frictional resistance of second layer, then frictional resistance of third layer, where perimeter is same but the lengths are different and delta value is different, K value is different and average effective stress is also different. Then we have to find the allowable load by taking the ratio of ultimate load divided by factor of safety. Next example, a concrete pile of 350 mm diameter is driven into a layered sand shown in figure. Calculate the allowable load on the pile. Assume factor of safety equal to 4, K equal to 1.2, delta equal to 0.75, NQ equal to 25 and N gamma equal to 72.58. So here also there are 3 types of soil and there is a water table also. So below the water table we should take the submerged unit weight. While preparing this effective stress diagram, we should take care of the unit weight. If there is any water table, then we should take the submerged unit weight for estimating the effective stress. Then here at the pile tip, the phi value is 32 degrees. So we should take the critical depth as 15 times the diameter, because we are assuming that the phi value below 35 degrees will be taken as 15 times the diameter. Then Q0 dash, so we have to calculate the Q0 dash up to a depth of 5.25 meter. Then it is coming as 87.4. Then we have to prepare the effective stress diagram and then we have to calculate the average effective stress for each layer. Then we have to find the delta value, which is equal to 0.75 times of phi. So here since the phi value is same, delta value also same. And because it is granular soil, we have to take the equation of granular soil and then we have to substitute the values. So then we'll be getting the ultimate load carrying capacity, that divided by factor of safety will give you the allowable load on the pile. So here in this problem, the pile is square in shape and the cohesion is varying. It is varying with depth. At the ground level it is 50 kPa and at 10 meters depth it is 70 kPa. Even the gamma value is increasing from 15 to 17 kilonewton per meter cube for this 10 meter depth. Alpha value is given as 0.9. So here, since we had to find the cohesion at the pile tip, we had to use the interpolation method and then we had to calculate the cohesion at the pile tip. So which is coming as 68 kilonewton per meter square. Then this value we had to substitute in the end bearing resistance. Here end bearing resistance is C into NC multiplied by bearing area. Bearing area is 0.45 square because it is square pile. Then alpha into Cu bar, average cohesion for this 9 meter depth. 9 meter depth over 9 meter depth, the average cohesion is 50 plus 68 by 2 into surface area, perimeter into length. Perimeter is 4 into B because it is square pile multiplied by length of the pile is 9 meter. So that we can calculate ultimate load and then allowable load. Next example, a square pile 250 by 250 mm, 15 meter long is driven into loose sand deposit. The shear parameters are C equal to 0, phi equal to 36 degrees and gamma equal to 17 kilonewton per meter cube above water table and 19 kilonewton per meter cube below water table. Assume K equal to 2 and factor of safety equal to 2.5. Also calculate the uplift resistance of pile. NQ is given as 60 and N gamma equal to 60.306. So here delta value is calculated as 0.75 times of phi and here the soil is same but there is water table at a certain depth. So first we had to prepare the effective stress diagram. So for the first layer, that is dry soil, we can take the bulk unit weight, but for the remaining soil we should take the submerged unit weight. Here saturated unit weight is given as 19 kilonewton per meter cube minus unit weight of water. We will get the submerged unit weight multiplied by thickness. Remaining thickness is 13 meter. So that we can calculate the vector stress at the bottom of the pile. And here phi value is greater than 35 degrees. So we have taken as 20 times that of diameter and it is coming as 5 meter. So Q0 dash value we should find up to 5 meter depth. Then we should calculate the average effective stress for both the layers and then we have to substitute in the equation to estimate the ultimate load and then allowable load. Then here it is also asked to calculate the uplift resistance. So uplift resistance is nothing but sum of frictional resistance and weight of pile. So weight of pile, because it is square pile, volume is 0.25 into 0.25 into 15 meter length multiplied by unit weight of concrete is taken as 25, so that we can find the weight of pile multiplied by the frictional resistance. Frictional resistance is this component, this second term, which is 1276.42. So that will be getting the uplift resistance. Another example is design a square RCC precast pile to carry a working load of 300 kilonewton with factor of safety of 2.5. The soil is loose sand up to a depth of 3 meter below ground level, which is underlain by a soft clay layer. The properties of loose sand are gamma equal to 14 kilonewton per meter cube, C equal to 0 and phi equal to 20 degrees. The clay has gamma equal to 15 kilonewton per meter cube, Cu equal to 50 kPa and phi equal to 0. Use alpha equal to 0.9 for clay layer and K equal to 1.5, delta equal to 15 degrees for sand layer. If there is pull-out force of 200 kilonewton, what will be the factor of safety? So here the load is working load is given as 300 kilonewton. That means allowable load is 300 kilonewton. And factor of safety is given as 2.5. So we can calculate the ultimate load equal to 300 into 2.5, that is 750 kilonewton. Then ultimate load can be calculated using the equation CNC into AB plus K into sigma VA dash tan delta ASI plus all point is U bar into AS. So this is the end bearing resistance at the pile tip. Since it is clay soil at the pile tip, we are taking only the cohesion contribution. Then for frictional resistance, so top layer is loose sand, so we should take the frictional resistance of granular soil and frictional resistance of clay soil for the second layer. So then when we substitute the values in this equation, we will be getting an equation in terms of B and L. So since L2 value is not known, we have to assume it as L2 only in the equation. Then we have to assume any one parameter, because there are two unknowns and only one equation. We have to assume any one dimension. So if we assume the width of the pile as 350 millimeter, then we will be getting the L2 value as 12 meter. Then we can calculate the total length, which is equal to L1 plus L2, where L1 is 3 meter. Then here it is also asked to estimate the factor of safety when the pull-out force is given as 200 kilonewton. So to get the factor of safety, we should know the uplift resistance. So here factor of safety equal to uplift resistance divided by pull-out force. So where uplift resistance equal to frictional resistance plus weight of pile. So weight of pile equal to 0.35 square into 15 is the length multiplied by unit weight of concrete. Then frictional resistance equal to these two terms, sum of these two terms, and then we can find the uplift resistance, which is equal to 753.4 kilonewton. So factor of safety with respect to pull-out force equal to uplift resistance divided by pull-out force, which is coming as 3.767. Suppose if the soil profile is given like this, then how to estimate the ultimate load carrying capacity? So here also there are 4 layers. So first we have to prepare the pressure distribution diagram. So we have to calculate the effective stress at the bottom of each layer, and then we have to create a tabular column like this to estimate the frictional resistance of the pile. For end bearing resistance, we should take the soil properties corresponding to pile tip. So at the pile tip, phi value is 35 degrees. So LC value is taken as 20 times that of diameter. So corresponding to 8 meter depth, we have to find the Q naught dash value. Then we have to substitute in the end bearing resistance equation, and then we should multiply with the area of the pile. Then for frictional resistance, we have to calculate the frictional resistance through each layer. So for each layer, we have to calculate the frictional resistance using the tabular column. So here for each layer, average effective stress is calculated. Then tan delta is calculated because the delta value is varying. Then surface area is also calculated because the surface area is different for different layers since the length is different. Then the frictional resistance is calculated, and then the total is taken, and this value is taken here in this equation, and then the ultimate load is calculated.